Alright everyone, new series of videos, new chapter, uh, chemical reaction stoichiometry in the mole. So let's get into it. I put an image here. I like to start all my new chapters with a lovely, pretty image. For this one though, I thought I'd use a bit of history around the discoveries that led to the concept of the mole, which we'll discuss in this chapter. So this one I chose is a lovely, I think it's an etching. It's Michael Faraday in his lab at the Royal Institution in London. So this would have been the early 1800s, and look at his lab with all these bottles here, doing all of his experiments. Very famous chemist and physicist, especially in electronics and stuff, in physics. Did some great stuff. Very pretty image. Anyway, inquiry questions for this chapter. From the syllabus, what happens in chemical reactions? That's very broad. Anyway, how are measurements made in chemistry? This one I like. Measurements. This is all about what this whole module is about, and this whole module is often called quantitative chemistry. Quantitative means putting a value to or numbers to. So really, what happens in chemical reactions broadly? Measurements. Making measurements and using those measurements to make predictions of how much product will form and stuff like that. Alright, let's delve into it. There's our syllabus points. They'll be throughout the chapter in yellow. I like to put those yellow boxes if you're familiar with my work. I wrote something down here at the bottom to give a bit of context. Let's see how it reads. So it was first observed that chemical reactions were very mathematical in nature when early chemists, so those working in the early 1700s, so that would be Priestley and stuff like that, if you know a little bit. I only know a little bit too, don't worry too much. They started doing reactions that involved gases, and they noticed that these gases were consumed or produced in set, fixed ratios, whole number ratios too. Like 2 to 1 and 3 to 1, and it kind of hinted at that there was some underlying mathematics to this chemical reaction stuff. Okay, so first beginnings of quantitative chemistry, and I like this bit. It hinted that matter was made up of small bits that combined according to rules. Okay, kind of like Lego. So it was first observed in gases because we'll learn in a chapter later on, gases do this. It's hard to tell in liquids and solids because the same amount of something doesn't tend to take up the same amount of space. But more on that later. So it kind of hid when it was solids and liquids, but it's really obvious when you do experiments with gases. So as I was just saying, quantitative chemistry, putting numbers to chemistry. So using numerical values like mass and amounts and stuff like that. So in chemical history, a large breakthrough came when they observed these mathematical relationships. And it led to the process where we can now predict the quantity of products, knowing the quantity of the reactants. So it's mathematical. I like this because matter itself is made up of little pieces of mathematics. Still up to some debate, but I'm siding on the kind of the side where every piece of matter, everything in the universe is actually just a tiny piece of mathematics. Alright, I'm trying something new with this chapter too, is around this chapter I'm going to pose this problem and we're going to work our way through it slowly once we gain knowledge on how to approach this type of problem. Okay, so consider the following reaction. What we've got here, aluminium bromide reacts with potassium to form potassium bromide and aluminium. Now we've got the skills to convert those into chemical formulas, so we can do a chemical equation for it, and we'll do that soon. So that's the start of the problem, but here in black, here's the quantitative part. If I had 5 grams of aluminium bromide, that's one of the reactants, how much potassium, the other reactant, would I need to extract all the aluminium, because aluminium is one of the products, okay? I want to convert all the aluminium bromide over to aluminium. How much potassium do I need, okay? If I've got 5.00 grams of aluminium bromide. Okay, one thing at this stage is consider, would it be 5 grams of potassium as well? I hope you're a bit skeptical and realizing that potassium and aluminium bromide are very, very different in weight, okay? So I'm a bit skeptical because different atoms have different masses, okay? So the grams, and what you'll get to through this chapter, grams are not so important to chemists. We don't like them as much. We tend to convert. Anyway, back to some earlier work. Okay, new syllabus point because we're in yellow. Relate stoichiometry. Okay, those big numbers that we use out the front of those equations, because we realize that it's not one molecule reacting with one molecule, it can be multiples of them. Relate stoichiometry to the law of conservation of mass in chemical reactions by investigating balancing chemical reactions and volume of gases in chemical reactions. Okay, so we're going to do a practical to do volumes of gases, and we'll see that happening. Balancing chemical reactions, we'll do that as well early on. Okay, so a reminder on the conservation of mass. So the law of the conservation of mass could be stated as matter is neither created nor destroyed during a chemical or physical change. It's just rearranged. Yeah? So, a way to express this is the beginning of the understanding of chemistry is that the mass of the reactants always equals the mass of the products. Because in chemistry, we're not changing the identity of the atoms. We're changing the way they're bonded together. Okay? They're swapping partners, they're doing stuff, but the atoms aren't changing. If it was to change, it would be a nuclear reaction, and we need much more energy to do that. But in the realm of chemistry, we're not changing the identity of the atoms, we're just changing how they're bonded together. So, the law of the conservation of mass, early 1700s as well, by those first chemists. Alright. I'm going to show you an example here. So, methane combusts with oxygen to form carbon dioxide and water, okay? So, here we go, a little problem. If I had 16 grams of methane, let me rephrase that. If 16 grams of methane is combusted with 64 grams of oxygen, you get 44 grams of carbon dioxide and 36 grams of water. Okay, there's some funny numbers there. They don't equal. 16 is very different from 64, and 44 is different again, and 36 different again. Where do these numbers come from? Okay, but we'll get to that soon. But we can see that I've done a representation here. Here's our methane, CH4. Here's our oxygen, O2. Carbon dioxide and water formed, okay? We're saying that if 16 grams of methane and 64 grams here of oxygen, we form 44 grams of carbon dioxide and 36 grams of water. So we could do that and observe that happening. And one thing you should observe is that on this side, we've got 80 grams of matter, 80 grams all up of methane and of oxygen. And at the end, once the reaction is finished, we end up with 80 grams of product, 80 grams of carbon dioxide and water. And that is because the identity of the atoms do not change, the bonding just rearranges. Okay, so matter is neither created nor destroyed, just rearranged. Okay, but there's trouble with this and representing a formula, and we're finding the chemical formulas of the compounds as well. Okay, we know, and they know, those early chemists knew that the formulas for methane, you have to forgive me, I haven't subscripted this terrible work. But these early chemists knew the formulas for methane was CH4, and the oxygen was O2, and carbon dioxide was CO2, and water was H2O, And the number of atoms on each side did not equal. Okay, look at this. Okay, although we're getting a reaction with methane and oxygen, we're forming carbon dioxide and water. That's all fine, but look at this. One example is there's 4 hydrogens on the left hand side, there's 2 on the right hand side. Okay, so it doesn't at first appear that matter is being conserved, but it actually is. So something's wrong here. Okay, they also observed that in reaction, products and reactants tended to react in fixed ratios. Sometimes these ratios weren't 1 to 1, but they were 1 to 1 and 1 to 3 and so on. Okay, this led to the idea that reactants products did not combine in 1 to 1 ratios, so they weren't saying that one methane and 1 oxygen produced 1 carbon dioxide and 1 water. They realized that it wasn't that simple. Okay, one molecule wasn't reacting with one molecule and producing one and another. It's a little bit more complex than that. And so they realized this thing called balancing, or that there was more than these molecules involved. Ooh, let me rephrase that. Not more than, there was more than one of these molecules involved. There was just these types of molecules, but there was more than one. Okay. So, when balancing chemical equations, we ensure that the identity and the number of reactant atoms were the same as the product atoms. So the same on both sides. And this suddenly gave the early chemists an understanding on how reactions occur. So the basic rules of balancing chemical equations are: you need to add in multiples of the reactant or product molecules until the number and identity of the atoms in each side is equal. And what I mean by that, in this example, if we want to get the same number of atoms on the left and the right, we can add in more methanes. But we can't add in more carbons. There's no carbons in there. We can't add in H2 to balance it out because there's no hydrogen in there. Okay? But we can add in more methane molecules, more than one. We can also add in more than one oxygen molecules, okay, into the reaction for our balancing purposes, but we can't add in anything else. We can't add in an oxygen atom. We've got to add in more oxygen molecules, multiples of them. Same as the products to balance, okay? I can't suddenly add in just a carbon atom. If I need more carbons in there to balance it out, it's not going to be provided by anything else but more molecules of carbon dioxide. And the same as with water, okay? So number 2, don't change the identity of any molecules in the reaction or add a new molecule in. All right. So for this example here, with methane and oxygen going to carbon dioxide and water, I've drawn up a little table down the bottom here. And it might be handy to do this early on when you're just learning to balance, because balancing equations is all about atom bookkeeping or atom accounting. We're counting them to make sure they're the same on both sides. So what I've done is I've put the reactants over this side under the reactants, so kind of divided in half, and I put a table of the products here on the right. And all throughout the equation, we're just dealing with carbon, hydrogen, and oxygen. So I've put the 3 different types of elements here. And what I've done is just from 1, 1, 1, 1, I've counted the number of atoms. So on the left-hand side, if there's 1 methane, I've got 1 carbon and 4 hydrogens, and from the oxygen 2 oxygen atoms. Okay, and on the right, I've got 1 carbon from the carbon dioxide, I've got 2 hydrogens from the water, and I've got 3 oxygens. I've got the 1 from the water and the 2 from the CO2. Okay. All right, I've scribbled all over it. Let's clean it up a bit. Let's take a look. Okay, so if we look at hydrogen, you can see on the left there's 4 of them, and on the right there's 2. To balance, we need to have them equal, so we need to increase the amount of hydrogens on the right hand side, and ideally we want 2 more, okay, to equal the 4 that's on the left hand side. And how we do that is we can add in another water molecule. Okay, if we add in 1 more water molecule, we can do that because we're not changing the identity of the reaction. It's already producing water. one of them, but we're going to say the reaction is actually producing two of them. And here we are, okay? So now, if we look at the hydrogens, and I put a box around it here, now we've got 4 hydrogens on the left and 4 on the right. The 4 on the right are from 2 molecules of water, okay? 2 molecules of water are produced. Now we've got our hydrogens balanced. But now you might see that the numbers of oxygens has changed because we've put one more oxygen on the right hand side. Okay? And so let's look at that. Okay. Oxygen is 2 on the left and oxygen is 4 on the right. We need 4 on the left now, okay? And we can do that by adding one more molecule of oxygen on the reactant side or the left-hand side. And here we are. Now we've got one more molecule of oxygen. We've got 2 molecules there. So there's 4 on the left and now there's 4 on the right, okay? We balanced our hydrogens earlier and now we can see that all up, the number of atoms on the left and the identity of them equals the number and identity on the right hand side. 1 carbon, 4 hydrogens, 4 hydrogens, 4 oxygens and 4 oxygen atoms, okay? But what we've got now is this chemical equation and it's now balanced, and what it says is 1 molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. It's not as simple as a 1-to-1-to-1-to-1 reaction, okay? And that's what I just said there. All right. So we can also write this another way, okay? We can start to write it this way. Okay, we can write our CH4 plus O2 plus another O2 going to CO2 plus 1 molecule of water plus another molecule of water. And this is where it mirrors the coefficients in front of algebraic expressions. We write that as chemists as, well, we leave the methane alone, but instead of O2 plus O2, we write 2O2, where the 2 is a big number, the same kind of font as the atomic elements there, okay? And the little subscript 2 represents the 2 that are in that molecule. So this big 2 in front of the O2 says I've got 2 molecules of O2, or 2 molecules of oxygen, okay? And we write the CO2, there's only one of those, and we put a big 2 in front of the waters because we've got 2 waters here, 2 water molecules, big 2 in front and the H2O. Whatever comes afterwards, you've got 2 lots of that, 2 water molecules. And so these are the numbers that we use in chemistry to represent multiples of molecules. Okay, another piece of information that chemists add to equations are the states. So the physical states of these chemical species. So this information may be given in a question, but we also have the knowledge to work out the likely state of a product or reactant using our knowledge of intermolecular forces. Okay, and how we represent them in chemical equations is we use a subscript, so like the lower number, okay, and we use symbols after each species in brackets, okay. So there's most of the ones that we deal with, there's a few more states out there, but most of the ones in chemistry on Earth are going to be in 4 states, okay, and one of them is technically not a physical state, but it helps us chemists out, okay, because it's so common and its features will be different. The first 3 are the obvious ones here that I've given: solid, liquid and gas. We're all very familiar with those. Okay, the symbol that we use for solid is the 2 brackets with an S, liquid, the L in between, and the G, a gas. Here I've got an example. So sodium chloride as a solid crystal, NaCl, and a subscript S. Magnesium as metal, subscript S. Iron chloride as the salt, okay, the solid crystal salt, subscript S. Okay, Liquid, example, subscript L after water. Look at mercury there, subscript L, and carbon tetrachloride, subscript L, because it's a liquid. Okay, then we've got gases like carbon dioxide, oxygen, and neon. Now the new one, that's not technically a physical state, but we use the same symbol in chemistry because the chemistry is slightly different, is this one, the AQ, which means it's aqueous, which means it's that dissolved in water. Now, water is very common in Earth. A lot of chemistry happens in water. Life started in water. So us chemists, we like to do chemistry in water too. There's many advantages to it. Okay, so sodium chloride, aqueous, subscript aqueous, is talking about solid salt dissolved in water. Okay, iron chloride dissolved in water. Notice we had it as a solid here. Carbon dioxide dissolved in water, because it will dissolve in water. It's the fizz in your drink. Okay, so aqueous state. So we can add these states to our combustion of methane reaction, where we've got methane, which is a gas at standard temperature and pressure, and oxygen the same, subscript G, carbon dioxide, subscript G, and our water molecules, subscript L. Okay, so we can add that little detail in. All right. So these numbers, and I'm going to highlight them, like there and there, that appeared, that were those large coefficients in our reaction, in our chemical reaction, we give them a special name, and here it is. It's called stoichiometry, or some people call it stoichiometry, or some weird variation on that. Stoichiometry. And that kind of hints at the ratio that these reactants to products are formed. Now, one thing to forget, not to forget, please don't forget it, is even though we don't put a number there, in front of our methane, there's technically, you can't forget that the stoichiometry is 1 in front, and 1 in front of the carbon dioxide. So where something is mentioned, but without a number in front, remember that the stoichiometry in front of that one is 1. And it tells us the ratio that these react in and produce in. So it's a 1 to 2 to 1 to 2 reaction, where it's 1 molecule of methane reacts with 2 molecules of oxygen to give 1 molecule of carbon dioxide and 2 molecules of water. And that's the stoichiometry. Okay. But, yeah, here's an important thing down here. I like this one. Okay. These are ratios of molecules to molecules. They're not a ratio of mass. Okay. Don't forget that. Okay. Not a ratio of mass. It's molecules to molecules. And because all molecules and atoms weigh different, it's not related to mass, these numbers. Okay. I found this online, this little analogy, the stoichiometry, while making a chocolate chip cookie recipe. If you're hoping to make 12 chocolate chip cookies, you got to use this 1 to 4 to half to 1 to a half ratio. But if you only want 1 cookie, you've got to divide it all the stoichiometry, or those ratios that you combine them, down by 12. So it's 1/12 of a cup, a third of an egg. Yeah, these ratios keep going, but the ratio stays the same. The stoichiometry stays the same. It's just multiples of them. Good chocolate chip. Oh, a food analogy. Food analogies are really good. Okay. So we're going to start balancing chemical reactions, and here are a few tips that I like to use. Okay. Whatever atom you start with, no matter what atom, you're going to have to start somewhere and choose out an atom to start with. No matter where you start, you will still end up in the same balanced equation. You will, if you do it correctly, end up with the same answer. Okay, there's only one correct answer, but there are many paths to get to the answer. Okay, and some of these paths are easier than the others, and with a bit of experience and a bit of advice from someone who's more practiced in chemistry, I hope I am, will kind of hint you towards the easier paths because we've learnt them the hard way. Okay, here, I like this tip here. Any element that you see by itself, either as a reactant or product, leave that element to balance last. Okay, I'll do a few examples with that. If you do it sooner, it's likely that you're going to have to change that number in front several times. But if you leave it to last, you'll only do it once. Okay, hopefully there's an example soon where you'll see that in action. Okay, we can add in stoichiometric fractions, okay, where we don't have whole numbers there. Don't freak out. They're a handy step. But what we tend to do is, after we've got the fraction and it's fully balanced, what we tend to do is then get rid of the denominator of any fraction. Say you've got one fraction in there and it's divided by 3, what we do is multiply all the stoichiometry by 3 to get rid of any fractions. It's a handy tool sometimes. Okay, number 4. If you have a polyatomic ion that appears on both sides, treat it as a whole unit. Instead of treating it as, say, if you've got sulfate, treating it first by balancing the sulfur and then the oxygen. If sulfate appears on both sides, treat them as you're balancing sulfates. It will save you a bit of time and a bit of heartache. Number 5 here. I see a lot of pain in students. If you reach a point where you can see that equation cannot balance, no matter what you do, and you're going around in circles and circles and circles, very likely that what you've done wrong is you've made an error in one or more of the individual chemical formulas, okay? You need to go back and check that you've got the formula for your ionic compound right, or your covalent compound. Put money on it, you've incorrectly identified the formula there of one of those individual compounds, and that's what's causing you the pain, okay? All right, back to our problem with aluminium bromide and potassium. So this one here, aluminium bromide, reacts with potassium to form potassium bromide and aluminium. If I had 5 grams of aluminium bromide, how much potassium would I need to extract all the aluminium? Okay, we haven't got the knowledge to deal with maths and all that yet, but we have got the knowledge from the first white part written to do a balanced chemical reaction, okay? So we can use our periodic table there as well to help us out, so always have it handy. Aluminium bromide. The formula for aluminium bromide, if you look at aluminium on the periodic table, it's in the group that will always have a charge as an ion as +3. And bromine as an ion, when it becomes bromide, will always have a charge of -1. So to have a neutral compound, you'll always need 1 aluminium ion to 3 bromides to equal 0. So aluminium bromide is AlBr3, okay? And because it's an ionic compound, I put the little subscript solid in there because I know that ionic compounds have very, very strong bonding. And so at standard temperature and pressure, there's not enough energy around to turn it into a liquid. It's very strongly held together in a solid. Okay, here's potassium all by itself as a solid. It's potassium metal, okay? And the product, potassium bromide. Potassium as an ion is a single plus because it's in group 1, and bromide in the halogens, -1. So you just need 1 of each to equal 0 and form a neutral ionic compound, KBr, 1 to 1. And again, it's an ionic compound, so I'll put solid under there. And the other product is aluminium, just plain aluminium solid there. Okay. What you can see though is on the left hand side, I've got 3 bromines in aluminium bromide. On the right hand side, I've only got 1 bromine in potassium bromide. It's unbalanced. I need to balance this equation, okay? And to balance it, I can see that if, I'm going to do it on the one above, I'm going to show you it in working progress. I'll get rid of my scribbles there. Okay, if I've got 3 bromines on the left, I need 3 on the right, and the only way I can do that is to bring in 2 more potassium bromides, so I have 3 in total. I can put a big 3 out the front of that potassium bromide. Okay. One aluminium, aluminium's good. I've balanced it. So all I've got left is the potassiums. I've got 3 potassiums on the right hand side because each potassium bromide brings 1, and I've got 3 molecules of potassium bromide. So I need a 3 out the front here to balance it out. Okay, and that's how I got this one here. And I've added the stoichiometry there where it wasn't one in the bold. Okay, so we can see that 1 molecule of aluminium bromide, notice I put molecule in there because it's an ionic compound, it's an ongoing matrix, but one of those base units, okay? I know it's not a covalent single molecule, but we just tend to kind of recognize that as chemists, okay? So we can now see that 1 molecule of aluminium bromide reacts with 3 atoms of potassium to produce 3 of those ionic base units of potassium bromide and 1 atom of aluminium. Okay, now we're going to leave it until we know how many molecules of aluminium bromide are in 5 grams, and we'll get to that soon. Okay, what we've got now is some examples, and I might start a new video on that one. So, thanks for joining me. I'll do the examples in a separate video of some balancing.